Okay, welcome everyone to another vibrant seminar. Today we have the pleasure to have Cynthia Bortolotto from ETH, I think, right?
Yeah.
And she's going to speak about Weyl sums with multiplicative coefficients in joint distribution. So it's with you now, Cynthia.
Thank you very much. Thank you for inviting me. It's very good to be back in South America again for a few minutes. So I will be talking about Weyl sums with multiplicative coefficients and joint distribution. So the talk is given in two parts. So we're gonna first start with joint distributions, and then we're gonna see that to prove what we want to, we need to study some Weyl sums, and yeah, and then we'll solve partially this first problem with some other problem here, and then I'm gonna briefly talk about how we deal with the left cases. So this talk is a joint work with Matteo Bordignon and Bryce Kerr. And to start, I want to just recall what equidistribution is. So we're gonna start with a sequence of points in 0, 1 here. And we say that sequence is equidistributed if whenever we count, we take an interval, A, B, inside the interval 0, 1, and we count how many points of our sequence are inside. We divide by the up to some n, and then we divide to n. When we take the limit, we expect that we have the size of the interval here. So equidistributed, it's just what we actually imagine when we say this word. It distributes well here. We don't expect to have some place where the sequence just agglomerates here, but it's well distributed along the interval. And a few examples of equidistributed sequences. So we have, we can take an alpha irrational number, and we can multiply alpha times n and take the fractional part. And when we vary n, we get an equidistributed sequence in 0, 1. This is perhaps one of the most simple examples, and then we can generalize it a little bit. And instead of just taking alpha n, we can take a polynomial here. So alpha 1n plus alpha d n to the d. And here we just need to suppose that at least one of the coefficients is irrational. And then we also get an equidistributed sequence. And another example is if we take square root of n and we take the fractional part, this is also equidistributed. And to prove this, we usually don't check this definition here, but we have something called Weyl criterions, where we have some other criterions to check whether a sequence is equidistributed or not. And that's perhaps the most natural way to check whether the sequence is equidistributed. And it says the following. So our sequence is equidistributed if and only if, for every integer h that is non-zero, when we sum e to the 2 pi I h times our sequence sigma n, and we sum up to n, this is gonna be little o of n. So this means that the limit when n goes to infinity of the sum here is, and we divide by n, and then this is 0. So we're gonna use this criterion to show equidistribution. And we're going to be studying a very specific sequence. And our story to why we're studying this sequence starts in 1963, while Hooley was studying the behavior of these sums here. So we sum up to an x for every n. The divisor function evaluated in n squared plus a. So the divisor function counts the positive divisors. Of n squared plus a. And here we are supposing that a is not a perfect square as well. And he was trying to get an asymptotic behavior of this sum here and a good error term. And while decomposing the sums, he was led to analyze this other sum here. So we define SHN as the sum of v between 0 and n, such that v squared is congruent to minus a modulo n. And then we have e to the 2 pi I hv divided by n. So what we're doing here, we're taking this polynomial x squared plus a, and then when we fix an a, we take all the roots of this polynomial mod a, and we sum here the e to the 2 pi I, this root divided by n. And when we sum over all n smaller than x, he got this asymptotic bound. So we get an x to the 3/4 times log squared of x. So here we have the sum up to n, and then we sum all the roots mod n of this polynomial here, quadratic polynomial. And then we have this 2 pi I h v divided by n. And then he showed this decay for this exponential sum. And he saw that this was actually another interesting problem. This could actually mean something about how these roots distribute. But to be sure that that means something, we first need to study this function that counts the roots, because we can show that this sequence of roots divided by n of this quadratic polynomial mod n is equidistributed if this sum here is little o of the quantity of elements that we are summing, which is the sum up to x of the number of roots of this polynomial. And this is actually true, but to see that, we need to know how this behaves, and we need to show that this is smaller than what we get here. This is bigger than what you get there, sorry. So we are led to study this sum here. So for f an irreducible polynomial in Z now, so we were fixing as x squared plus a, but now let's just take an irreducible polynomial. And we define this function, whole f of n, that counts how many roots to this polynomial mod n we have. And one can easily see that this function is multiplicative. So that means that if we take an n, n1, and n2 that are co-prime, this function evaluated in the product is the product of this function evaluated in whole f of n1 times whole f of n2. And this is just a consequence of the Chinese remainder theorem. And we can actually use that this function is multiplicative together with the Weier's theorem to show that when we sum this function up to n, this is asymptotic to a constant times n. This constant depends on the polynomial that we're considering. So what Hooley did was actually show that these sequences given by these ratios here are equidistributed because this sum here is asymptotic to a constant times f. So just to make it clear, what he did is he showed that when we sum this for all age non-zero, we have something that decays faster than the sum of all elements here. So that means that if we consider the sequence of n for whole squared v squared congruent to a mod n, and then we vary n, this sequence here is equidistributed. And just to be clear, when we fix n, we can have several roots. So the way we do it, we consider the sequence where n is in ascending order. And here we can actually put the roots, order the roots the way we want to. It doesn't make a difference. So with Weyl's criterion and Hooley's result, we can conclude that. And then one could ask what happens if the degree of our polynomial is bigger than 2, because now we were showing that this holds whenever f is of the form x squared plus a not a perfect square. But it's natural to think what will happen when f is not a quadratic polynomial, it has degree greater than 1. Are these roots still equidistributed? And that's what Huli showed the year after. So if you consider f an irreducible polynomial of degree e bigger than 1, then when we sum n up to x, and for each n we sum this exponential sum e to the 2 pi I h times v divided by n for all v roots mod n of this polynomial, this decays faster than x. And this implies that these roots are also equidistributed in the Weyl sense. And here the methods are quite different. We know that we lose a lot of decay when we don't, when the polynomial is not quadratic. When it's quadratic, we have an x spare here, x to the 1/4, except for this log factor. But here we lose a lot of decay, and the techniques are quite different. So when we have a quadratic polynomial, we rely, we can associate this to quadratic forms and use this very strongly, and we get this decay there. But in this case here, we just use something very different. We use some multiplicativity property of these sums, and they rely very strongly on the Chinese remainder theorem. So what he did was he proved this. So when we take k and p prime coprimes and we multiply this sum here, we have some multiplicativity property, and together with Cauchy-Schwarz and splitting the sum in small primes and small divisors and big divisors, he managed to prove this inequality here. Note that the inequality that he proves is stronger actually than what he needed. So to prove equidistribution of these roots, we just need to analyze this function, these sums here, and to prove this. And he managed to prove something stronger than that. So he managed to actually put the modulus inside the sum here. So we have actually something a bit stronger than what we needed. And that's going to be necessary for what we're going to do afterwards. So an observation is that the theorem also holds for non-irreducible polynomials. One could show that just adapting the proof, but the result also holds. So we know that these sequences, these roots are equidistributed, but we could try to get more information about it. And there's quite a lot of work in this. I just want to point out these two works. So the first one is a famous work of Duke, Friedlander, and Ibanez. They proved that the roots actually distribute well when we only consider the roots modulo primes. So they showed that when we sum for all primes is smaller than x, then we consider v squared congruent to minus a modulo prime. And we take this v here in ZPZ divided by p. This is little o of x divided by log x. And they managed to prove that this is true for quadratic polynomials as well. But no one knows how to deal with the case where f is some other polynomial that's not quadratic. And the techniques that they use to prove this relies very much on the fact that this is quadratic. And some other work of Kowalski and Sound, it's quite recent. They proved that we have some equidistribution from the Chinese remainder theorem. So now we don't necessarily need to consider, we have some sets xn that are not necessarily for each n roots of a reducible polynomial, but they do satisfy some property involving the Chinese remainder theorem. And then we can also prove some equidistribution. So there are some other works, but I'd like to point out this too. And our attempt to better understand these roots is the following. So let's call GK the sequences of the ratios. And let's take another sequence, AK, that we know that is equidistributed in the Weyl sense as well. And then we can ask how this new sequence, GK, AK, distributes in the square. So thing is, we take our original sequence here, and then we pair with another sequence, and we want to know if they are equidistributed or not. And we observe that if we prove such a result for a sequence AK, we are showing that our original sequence and the sequence AK are not correlated in some sense. So that's what we want to prove. So our goal was actually to take this sequence as polynomials evaluated in n and see what happens. So that's what we proved. So let me make it more clear. So now we start with another polynomial with real coefficients. So big F of x, alpha 1 of x plus alpha d of x to the d. And we suppose that this d is bigger than 1, or at least 1. And we suppose as well that at least one of the coefficients is irrational, because we know that this sequence Fn is only this equidistributed if one of the coefficients of this polynomial is irrational. And then we define this new sequence in the square as follows. So when we fix 1n, we take all the roots mod n. So this is the first root, the second one, and so on. And then we pair this with f of n. So here's f of n. And then we take this. And we do this for every n to generate this new sequence. And what we showed is that for every polynomial like this, with at least one irrational coefficient, it holds that this new sequence is equidistributed in the Weyl sense. Observe that from Weyl's criterion, it suffices to show that when we sum for every k and h non-simultaneously 0 in Z2, if we sum up to x, e of k e to the 2 pi I k times f of n, big F of n, so our polynomial here, times this sum over the roots mod n of e to the 2 pi I h, the root divided by n, this is little o of x. It is enough to show this by Weyl's criterion. And we observe that Huli showed that this holds with the modulus inside the sum here. So whenever h is different than 0, we can just use Huli's result and the triangle inequality here. And then we get exactly this. So we just use triangle inequality and we get rid of this exponential sum here. And then we have this sum over all the roots, mod n to h times b divided by n. And we just apply what Huli showed. This is little o of x. So this case is handled. So the only thing that we need to show, we need to see what happens when h is equal to 0. So when h is equal to 0, we'll be summing here the number of roots that we have mod n. And here we have this exponential sum times the number of roots, which we define to be O f of n. So we get this. We have this exponential sum, and here we have this exponential, and here we have a multiplicative function. Recall that Fn is this polynomial with at least one irrational coefficient. And now we want to study this. So this exponential sum with a multiplicative coefficient. And this is actually an area of study of its own. So if we have, let's forget a little bit about this function that counts how many roots we have mod n, and let's take any multiplicative function. And then we ask the question, how does the sum up to n of this multiplicative function gn times e to the 2 pi alpha n behaves? So can we say, for instance, something like this? This is little o of the sum. So this is an ongoing area of research. So I'll start with, I'll just cite a few results. So the Bossi first showed that if G is bounded by 1 and we approximate alpha but by A divided by Q, where A and Q are co-prime, and we suppose that Q is small compared to N, then we can prove that we have such a decay. So this multiplicative, this exponential sum with this multiplicative coefficient G loses to N divided by log Q to the 1/2. And Montgomery and Vaughan in the 70s showed that if we have a multiplicative function that is bounded on primes, and if we suppose that the sum of the squares lose to n when we sum up to n, then we can also get some decay. So it is as follows. We again approximate, take approximation of alpha, and we suppose that our Q is bigger than 1r and smaller than n to r. R is just a parameter here. And then we can prove that our sum loses to n divided by log n plus n times log r to the 3 halves divided by square root of r. And this term here is sharp. One can find quite a lot of examples of multiplicative functions that attain this n divided by log n, but this term here, we don't know exactly what's the optimal dependence on R and what should it be. So it's an open problem. And it is expected that one could get rid of this log R to the 3 halves. So recently, Bretach and Granville studied these sums very in detail in the minor arcs, and they conjecture that such a result should hold as well. So here we have the n log n, and then we have n divided by q to the 1/2. 1 plus here is alpha minus a divided by q times n. So we expect something like this to be true. And as I said, this is an ongoing area of research. And when we were trying to solve the problem, we thought that maybe we could apply Montgomery and Vaughan's result to get something. But we see that some of the hypotheses fail. So here are the hypotheses. Here is Montgomery and Vaughan theorem. So the first thing that we should check is for a function that counts the number of roots mod n of a reducible polynomial, when we evaluate it in a prime, is it bounded by constant for every prime? And this is true in our case, because we know this is always going to be bounded by the degree of the polynomial. Then we ask whether when we sum this function, this loses up to n, this loses to n. And this is also true in our case. And then Montgomery and Vaughan, they require that this is true. So when we sum the squares of the function, this loses to n. And this is something that we don't have. Because when we make the degree of the polynomial higher, we can have an extra log factor here to some power a, and we have zero control of a. So a can be anything. depending on the polynomial. So this is something that we don't have. And we observed that in Montgomery and Vaughan theorem, we also had alpha times n in the oscillation, and we want to generalize this for any polynomial. So we don't have this as well. So our first goal is generalize Montgomery and Vaughan result, where we can make this hypothesis of the sums of the squares a bit less restrictive. So we can add the power of log, any power of log, and then we can also change this alpha n to any polynomial in the oscillation factor. So that's what we did. So we proved that for any a and c real numbers and g multiplicative function satisfying the following conditions. So g evaluated in primes are bounded by c. The first, the L1 norm of the function is bounded by n. And when we take the L2 norm, we get at most n log n to some power. And then if we take any polynomial here with one irrational coefficient, and suppose that there exists L, A, and Q, and here we take Q smaller than R, A and K coprime, such that one of the coefficients is well approximated. So alpha L minus A to the K loses to 1 over R divided by K. Then for every R bigger than D times D plus 1, we have this expression here. So it's much uglier than Montgomery and Vaughan. So let's make some observations here. So this R is a parameter. We can take it as big as we want to, but the constant here will depend on R. And we have this C here, which is A plus 1 divided by 2R. And we observe that when we take R very big, then we can make this C smaller. And the first term here is log n to the 1 minus C. So we lose this decay here of log to the C. And we can make it small, but then we lose in the constant. And also this A here, like it's something that we cannot prove this is optimal. So the counterexamples that we used to show that this n divided by log n is optimal don't work here. But we have this factor here. And then we have this ugly expression. So log of n to the c times q divided by n to the l plus 1 over q to this power here, 1 over 4, 1 r squared plus this term here. So the important thing is that when we take q in some similar range as Montgomery and Vaughan did, so this would be our R. So we take q between R and n to the L divided by R, then we get this decay. And we only lose a little bit here. So this C, which we can make as small as we want, of course, but losing within the constant here. And so that's the result. And we observe that if we can approximate for every n one of the coefficients by some QAL to divide by QL, where QL is big enough, then we get what we want for our function. So our exponential sum here, for f of n times e to this polynomial in the oscillation factor, will lose to, let's say, n divided by log n to the 1/2. And we just need to make sure that we can approximate at least one of the coefficients by a q here, where the q is large enough, depending on n. So that's the first approach. So we try to solve our problem by using this result, but we see that there's this problem when we have irrational numbers with small approximations. It's not possible using these methods. So we cannot push through this and make the result valid for most because of this expression here. So so we solve partially the problem. And I will give an idea of the proof. So it's based on Montgomery and Vaughan's result, as I said. So just a quick idea of how it goes. So we want to explore this sum here. The first thing that Montgomery and Vaughan had the idea to do was to reduce it to bilinear forms. So here we use Holder and Möbius transform to get this inequality here. So we have that the sum loses to n, log n to 1 minus epsilon, plus 1 over log n times this sum here, where we are summing over all n integers and all p primes, such that n times p loses to n. And we are summing our function, multiplicative function g of n times g of p. We have a log p here, and then we have our oscillating factor e to the g n times p. So we're basically looking to this sum now like this. So we have the hyperbola here, and one of the x's we take on the primes, and the other one we take the integers. And then we want to see what happens to the sum here in this area. And what Montgomery and Vaughan did is they split this hyperbola in several rectangles. So what you see here is that we always split the integer side by half. So we have 1 up to n, we take the half here, and then we go up to 1, and we consider this first rectangle R1. And then we do the same thing. So we take n divided by 4, and then we walk from n divided by 2 up until 2. So we touch the hyperbola, and then we consider this rectangle here, and so on. And then we keep doing this process. So here you might not believe, but this thing here is half of this. And we split in half, we walk until we touch the hyperbola, and then we consider these rectangles here. And we keep doing this up until a parameter. And the idea is we analyze the sum over the rectangles so we can exploit more the oscillation there. And afterwards, we just sum up and use that they are disjoint. And for each rectangle, the way we bound the sums is using basically a lot of Holder together with Vinogradov's mean theorem that counts how many integer solutions we have to this system of equations here. So for every j between 1 and d, we have v1 to the j plus vr to the j equals to vr plus 1 to the j, and so on, up to v to the 2r to the j. And we want to count how many solutions we have to that. And using this, we can analyze this sum here in the rectangles, plus a lot of Holder. And summing up and estimating, basically we get this first result. So To conclude, I just want to give an idea of how this works when we are not in the range where this theorem can cover. So recall that we want to show that this sum here is little o of n. And we manage to do this whenever we can well approximate the irrational coefficients by some big enough denominator QL here. And then the results follows. But to prove the result, we actually have to analyze when we suppose that for all approximations that we get using the Dirichlet's theorem, they will all be small compared to n. And we have to use very different methods for this case. So the proposition is that when this happens for all I, so ki loses to log n to the b for all I, then we still have some decay that is good enough. So n to some power of divided by some power of q. So since we know that at least one of the coefficients is irrational, we can take q to infinity. So this is good enough to show the result. And to prove that, what we do is we integrate by parts, and we have to analyze now these sums here, where here we have our multiplicative function, and here we have a Dirichlet character, mod a divisor of q. And we want to analyze how this decays. And in order to study this, we actually analyze the Dirichlet function, where the coefficients are our multiplicative sum times the Dirichlet character. And so very briefly, what is interesting about this is that this function rho of f is actually the number of fixed points of the Frobenius automorphism in the Galois group of the splitting field of this polynomial f. So I know that's a lot of information, but what is interesting is that we can analyze this Dirichlet function by using some theory of Artingel functions. So we can sort of write this as some other function here, f of s, where we can control. And using this fact here, we can write this as a product of some powers of Dirichlet Artingel's function, sorry, to some powers. And then we use what we know about Artingel functions to analyze the decay of this L function near the line s, real part of s equals to 1. And we can show some result like this. So we can show that this sum of these characters times this multiplicative, a function that count the roots, behaves like n to the r times something that is controlled, and most of the times is 0, plus this error term here. And we can use that to show that when the q's are small, we also have decay enough of those exponential sums with multiplicative coefficient. But observe that this only holds in this case where our multiplicative function is counting the number of roots mod n. And then we can conclude the proof of the equidistribution theorem. Yeah, I think that's it. Thank you.
Thank you, Cynthia, for the nice talk. We have time for questions. Does anyone has a question?
Well, I do have a question.
Go ahead.
So can you go back for the first page where you said Hooley proved equidistribution for the roots of quadratic polynomial, and then in the following year for a generic degree, right?
Yeah.
But that congruence was congruence to an integer, and then sometime later, three guys proved congruence to prime modulo for a quadratic polynomial, and so the quadratic case in the prime modulo case is also based in the theory of quadratic forms, because you said Huli based his proof in the theory of quadratic forms, probably because they're positive definite quadratic forms. I don't know. So the prime case, they base their proof in the theory of quadratic forms also.
Yes, it was much more involved than what Hooley did. So Hooley did just some counting argument, and they use hyperbolic geometry to prove the prime case. So it's much more involved, but it relies very strongly in the fact that we are dealing with quadratic forms. And yeah.
But and then Hooley in the generic case, for the generic degree, the proof is based on what? I mean,
so it's based. It's basically the Chinese remainder theorem. So we can prove something like this. We can split when we take two co-prime numbers, k and prime. If we multiply these sums here, so SHK, which is the sum of the roots mod k.
Yeah.
By the same sum with another key prime here, we have this identity, just using the Chinese remainder theorem. So what he did was he split the sum when we're summing in small divisors and big divisors. And then he used this identity here to exploit better the decay. So it's basically just the Chinese remainder theorem, the main key of the proof.
Okay, thanks. That was my question. Thank you.
Hi. So actually, I just thinking about this result of Montgomery and Vaughan. This average, if you consider in short interval, is this kind of result is known?
Sorry, if they?
So yeah, so in the result of Vaughan and Montgomery, so the instead of considering long average, the short average kind of result is known.
I don't know. Yeah.
I mean, even same question is valid for your result also, right?
Sorry, I didn't understand.
Yeah, so I mean, all result is kind of a long average, right? You're taking say n up to x. So instead of taking n up to x, if I taking n lies between n to x plus h, where which is certain size we define for h. So this kind of result is known.
I don't know if this case is done. Yeah.
Let's see. Okay. Thank you.
Okay, does anyone has another question? Okay, so thanks a lot, Cynthia. I'll stop to recording now.